Hello everybody, welcome back to The Joy of Coding at Portland State University. Let's continue our exploration of the Java programming platform with an overview of the fundamental structures that Java provides for object-oriented programming. If you've done OOP in languages like C++ or Python, most of these concepts will likely be familiar to you. However, Java offers some unique language syntax that helps developers express the state and behavior associated with objects and their classes. So as we've seen, the fundamental unit of programming in Java is the class. And classes contain methods that perform work. Remember back to Hello World, we had the main method which prints out hello. That's what the methods do, they perform work. Now, as you've probably learned in other classes about object-oriented programming, classes can be instantiated to create something called an object. So an object is said to be an instance of a class, and an object represents, well, a piece of data in your program. Representing data in programs is nothing new, but what object-oriented programming provides is a separation between the notion of what work is to be done from how that work is done. So the what part of an object is the methods that a class provides, which really gives a contract that can be used by another piece of code. Right, so another piece of code will invoke a method according to its signature. Right, the signature of a method is the name of the method plus its parameters and its return type. And of course, all of these parameter types have their own semantics, their own meaning of here's what an int is, here's what a string is. So the contract describes what the method does. And the implementation of that method, the how of that method, may be unique to each class that implements that method. A key mechanism for maintaining the separation between what a method does and how it does it is something called a virtual function. With a virtual function, the choice of what code to execute is left until runtime. If you go back and study older programming languages, at compile time it was pretty much known exactly what code would be run. And while that made for very efficient execution, it didn't give you a lot of choice at runtime. And with objects and object-oriented programming, it's all about leaving the choice until runtime to determine exactly what method is being invoked. So when you invoke a method on an object, the choice of implementation is made at runtime based on the specific type of the object on which the method is invoked. Again, this is called a virtual function or a dynamic dispatch operation that is performed. In addition to methods, classes have variables associated with them that are called fields. And there are two kinds of fields in Java. There's something called an instance field, which is a piece of data, a variable that is associated with each instance of the class, with an object. There are also fields that are associated with the class itself. So no matter how many instances of that class are created, how many objects of that class exist in the system, they all share the same value of that class field. In Java, class fields are denoted using the static keyword, which means that it's static across all instances. You'll be seeing a lot of Java code in this course, and there's an important convention that you need to be aware of. By convention in Java, class names begin with a capital letter, like employee, or we saw a capital H hello. Field and method names, however, begin with lowercase letters, so you'll see fields like name, or methods like main, lowercase. Object-oriented programming is all about abstracting data and providing access only to the data that's interesting, and whether that data be fields or methods. And the way you implement that data encapsulation is through access control. And Java provides a couple of access control modifiers that allow the developer to specify what other code ought to have access to the particular method or field or class. So a field or method that is declared as public is accessible anywhere the class that contains it is accessible. On the other end of the spectrum, a private method or a private field is only accessible by the class in which it is declared. no one outside of the class can use it. Hopefully you've heard about inheritance in object-oriented programming and that you can have classes that subclass another class. The protected keyword allows methods and fields to be accessible only by direct subclasses and classes in the same package. If you don't provide any access control modifier for a field or a method, it is said to have default level access, which makes it available to all other classes in the same package. This is another feature of packages. Not only do they group classes together, but you can also use a package to control what other classes have access to a particular field or to a particular method. There's a special kind of method called a constructor, which is used to initialize a newly created object. So basically, this code is invoked when the class is instantiated, when a new object of that class is created. And in Java, you instantiate a class using the new operator. So you say something like, new employee. Constructors have the same name as the class whose instances they initialize. So the employee class, capital E employee, will have a constructor named capital E employee. Constructors may take parameters, and as we'll see, there are some values that are passed in or required when you create an instance of an object. But constructors don't have return types, so they're not really a method in that sense. Again, they initialize an object when it's created. And when you use the new operator, the Java virtual machine allocates a little piece of memory for that object on the JVM's garbage collected heap. We'll talk more about garbage collection in a moment. Now, methods are code that executes, and what the code often does is manipulate something about an object, maybe change its state or perform some other operation on behalf of that object. Again, objects have behavior that are expressed as methods. Methods can have parameters that provide information to the method, and they can also declare they return some value, so they have a return type. If a method doesn't return any data, it has a return type of void. And I think now we've learned enough to understand what public static void main is all about. You've got a method called main. It is static. It is associated with a class, not an instance of a class, right? We didn't have to create a new hello in order to invoke the main method. It's public, meaning that the main method can be seen anywhere that the hello class can be seen. And it doesn't return a value. So it's got a type of void, public static void main. Now, when you want to invoke a method, you do it on an object, or as we'll see, a class. So the whole idea is that there is a receiver of that method, and you pass parameters to it. So down here at the bottom of the slide, there are a couple of examples of invoking methods. The first method is a class method, is a static method called now on a class called localDate. This is a class that we'll learn about in later slides. That basically represents, a point in time, a date. And so we call capital L localDate.now and assign it to a variable called now of type localDate. And the way we obtain that instance of localDate is by calling localDate.now. This API doesn't provide a constructor. Instead, it uses static methods, class methods, to create objects. Once we've got one of those objects, however, we can invoke an instance method like -days. So we can say not now.minusdays of 1. It'll pass that value 1 to the -days method. And that -days method returns a different local date object that represents, the date yesterday. Now, most well-behaved objects, if they have state which can be changed, so-called mutable state, they want to protect access to that state, to make sure that the state is properly encapsulated so that if someone is going to change it, it's the object itself that ultimately determines how it should be changed and if the value that's changed to is valid. So a good rule of thumb is that you shouldn't have public fields in your classes. Instead, have methods that do the work of the class and then access the state to maintain whatever data is valuable. So here is an example of a class called employee. And it has a mixture of both instance fields and class fields. So we start out with 3 instance fields. And you know they're instance fields because they do not have the keyword static. You have an ID field in the employee of type int. You have a name of type string. And then you have a boss. So this employee refers to another employee. And it has an initial value of null. The employee class initializes the employee's ID from a global counter. So every time you create an employee object, you increment that global counter and assign it to the ID of the particular employee being created. And this is done in the constructor. So if you look at the constructor, and that's that method that starts with public employee, it takes a string, which is the name, but note that it doesn't have a return type. Again, constructors don't have return types because they don't return a value. They merely initialize the fields and perform other work when the employee is instantiated. So what the employee constructor does is it assigns an ID to the newly created employee by incrementing the value of the static next ID field. And then it assigns the name for this particular employee to the value that was passed in to the constructor. So there we say this.name equals name. What that's doing is assigning the value of the name parameter to the name field in this particular instance of employee. This is a convention that you'll see me use a lot. You'll have a constructor that has a parameter that has the same name of a field, and we simply assign it inside the constructor. Now, each one of these fields, as we mentioned, is private because we don't want anybody to be able to change them. We want the employee to ultimately have control over how its fields are accessed. For fields that are mutable, that are meant to change over time, like an employee's boss, we provide methods that will set and fetch the value of the boss of an employee. And those methods are called setBoss, which takes a boss object and assigns it to the boss field, and getBoss, which really returns the value of boss. This is a common pattern in Java programming and lots of object-oriented programming languages to have these so-called accessor and mutator methods for an object's fields. Now, the signature of a method consists of the method's name and its parameters, the type and number of parameters of the name. In Java, you can have multiple methods on a class that have the same name but take different parameters and therefore have different signatures. So for instance, for our employee object, we could have a setName method that takes one string for the entire name. Or you could have a setName method that takes a string for the first name and a string for the last name, and the implementation of that merely concatenates the two strings together using the plus operator and assigns it to the name field. In this case, where we have two methods with the same name but have different parameters, we say that the setName method is overloaded, meaning that it's overloaded with different arguments. In the employee class, we saw that the next ID field was a static field, a class field, that was associated not with a particular instance of the class, but with all instances of the class. Let's talk a little bit more about static fields and what they do. Now, the values of static fields are initialized before basically very early on in the class's lifetime. So before any instance is created or before any static field is referenced, the other static fields or a static method is invoked, I guess, is a better example. The values of the static fields are initialized. In the example with next ID, the initial value is 0. That is kind of the default value, not very interesting. If you want to do more things as part of initializing a class, part of initializing static fields, you can do so in what's called a static block. So here is an example of a class called day that has a static field called days of the week, which is an array of strings. And we want to initialize that. We initialize it in what's called a static initialization block. So you have the keyword static and then followed by a block of code. And there we set the days of the week to have an initial value of a string array of length 7, and then we populate the contents of that array with the days of the week. So element 0 is Sunday, 1 is Monday, element 2 is Tuesday, etc. Now when we want to reference that days of the week, we have the name of the class. Remember, there's no instance of the class here. It's just the class itself, capital D day, dot days of the week, and then Monday is going to be element 1. So that's the way that we reference it outside of the class. Just like we saw that the static field is referenced using the class and non-instance of the class, a static method is invoked with respect to the entire class and not an object. So if you have a method that has the static keyword before it, it's said to be a class method. Again, associated not with an instance, but with all of the instances of the class. The interesting thing is that static methods, there's not a this variable. This only refers to an object. And as a result, a static method cannot invoke an instance method within a class, even though it's the same class, even if it's private. A static method can't invoke an instance method because there's no object on which to invoke the instance method. And then here's an example of a static method which gets the day at a particular index and returns that string. And what it does is it references the days of the week static field. A static method can reference static fields. And the way that you invoke the method is that you say capital D day, which is the name of the class, dot get day with a value of 1. And that returns Monday. Because static methods aren't invoked against an instance of a class, they're more like functions in C, right? You can just call them. And Java has a language feature that allows you to import static members of classes so that when you reference those members, when you call that method or that when you access that field, inside the code, you don't need to prefix it with the name of the class. And here's an example of how to do that. After our package statement, we have two import statements. And these are static imports because they say import static. And then what you give is the name of either a class, all of whose static members you want to import. Or in that second import static example, you say you want to import one static member of the Java Lang system class, and that's out. And so then what you can do, as you can see here in the main method, is that you can reference static members of the classes that you've statically imported without prefixing it with the name of the class. Instead of having to say integer.parseInt, you can just say parseInt. Instead of saying system.out, you can just say out. Similarly, integer.maxValue can just be referenced as max value. This can help declutter the code and sometimes make it easier to read, although sometimes I've found that doing these static imports, especially if you're not familiar with the methods that you're invoking, can kind of make it hard to guess, because when you see parsing, you're not too sure exactly where that code comes from. Sometimes that's okay, and sometimes that can be confusing. It's really at the judgment of the developer to determine whether or not static imports make sense in a particular context. A couple slides ago, I mentioned that the new operator allocates memory for an object on something called the JVM's garbage collected heap. This speaks to how memory is managed in Java. Now, if you're coming from a language like C or C++, you're used to thinking about memory allocation and deallocation. Right? In C, you use malloc and free. In C++, you create objects with new, and then you destroy objects with delete. But as we've all experienced the hard way, when you get memory allocation wrong, bad things happen, right? You either clean up objects before you're done using them, and then you end up referencing data which is bogus, broken, your program crashes. Or you don't clean up the memory when you ought to, and then you end up taking a lot more memory and system resources than the program actually needs, and that's not a good thing either. Well, in Java, memory management is taken care of for you, or at least the cleanup process is taken care of for you. There is a process that runs in the background of the JVM called the garbage collector, which will look for objects that have become garbage and delete them to free up memory for use by other objects. So an object is considered to be garbage when it meets a bunch of criteria. First of all, the object is not referenced by a static field. Objects in static fields stay around as long as the class stays around, and the class stays around essentially forever. An object is also considered garbage when it is not referenced by a variable currently in an executing method. So if a method is executing and it's using an object, well, that's live, right? It's most likely going to be used again because it's in a currently executing method, so it's not ready to be cleaned up yet. And then it's also garbage if it's not referenced by another live object, basically meaning that you have what's called the transitive closure. And you have all the objects that are referenced by static fields that are currently executing methods, and then all of the objects that those refer to and the ones that they refer to, right? You create this whole map, and those are all the live objects. Anything that isn't reachable from a live object is considered garbage. And while this certainly takes up some amount of work for the JVM to maintain all of this, the developers really reap great benefits because we're not responsible for cleaning up after ourselves. Someone else does that for you, right? So there is no delete operator in Java. There is no free function to call. Instead, the JVM cleans up after us for us. So as a result, you don't end up with dangling references. You don't end up with a pointer that points off to nothing or even worse, some other object. This makes the language a lot safer. Java programs don't crash in the same way that native C and C++ programs do. However, I've had people say, oh, let me do memory leaks. Well, you can still have memory leaks. Remember what memory leak is data that can be cleaned up but isn't cleaned up. And you can still have this in Java if you again hold on to things in especially static fields when they don't really need to be held on to. So you can, if you have an object that even though you're never going to use again, if you're keeping it alive for some reason because the program is still holding on to it, you're going to get a memory leak. So you still need to be careful in terms of what objects you store for the long term. But anything that's created temporarily or has limited lifespan will be cleaned up automatically by the garbage collector. Now, in object-oriented programming, you've probably learned about inheritance and the fact that you have a class and you're going to have classes that inherit all of the capabilities, the behaviors, and the state from another class. And this is great for code reuse, right? It allows you to take pieces, parts from other aspects of your program and reuse them very easily. When you think about what a class provides, there is the contract that is available through the methods and fields of a class. And when you extend a class, you inherit all of the contract from your parent class. That's great because it can come with implementation. It can also just say, hey, listen, this is behaviors that I, as a subclass of that other class, need to provide. Note, though, that while a subclass can change how a particular behavior is implemented, how a method is implemented, it shouldn't change the semantics of the contract. It should still mean the same, which means that, you should be think twice before adding additional error checking or by performing drastically different operations. When you subclass another class, when you inherit behavior, or when you override behavior, which we'll talk about shortly, you should make sure that the contract is still the same because of that dynamic dispatch, because of the polymorphism that's available in object-oriented programming. The client who is invoking that method doesn't necessarily know what code is going to be executed. So it's really important for you as a developer not to change the contract because it'll have surprising side effects for the people that call the code. I mentioned polymorphism just now. I didn't say what it was. The fact that a subclass of a class can be used wherever its superclass can be used, this is polymorphism. Meaning that, hey, listen, right now I'm dealing with something more abstract, but concretely it could be something else. I don't really care. I'm programming to the interface provided by that superclass. That's all I'm going to use. The fact that at runtime it's some other object, I don't really care right now, but because of polymorphism, things will work as I expect. More concrete example is the following. The fact that in Java everything is an object Java Lang object is the root class of all other classes. It means that if I have a variable of type object, I can assign whatever I want to it. So I start out with a string called s. It's a string. That's great. Because a string is an object, I can assign that string variable to the variable o of type object. And now if I have code that's using o to call methods on object, everything will work because a string has everything an object has. We'll be seeing a tremendous number of examples of this in contemporary software development as we learn about object-oriented programming and as we explore the Java language API. So we talked about how inheritance works. You have a class which is a subclass of another. Java also has this concept of final, meaning that if you mark a class as final, no other code can subclass that. This is important. There are some times where you want to prevent a class from being extended or a method from being overridden by a subclass. So for instance, let's say you've got a method that performs something that's very security sensitive, like validating a password. You don't want another class to override that validate password behavior to always return true. It's like, yep, it's always valid. That defeats the entire purpose. Definitely you're changing the contract of a method in that subclass. So in order to prevent that scenario, we mark the validate password method as final, and any code that attempts to override that will simply not compile. And because of this, we can be confident that the validate password method will always execute as implemented. The final keyword can also be used with fields. So if you mark a field as final, it means that it cannot be modified after its initial assignment. So final fields can only be initialized in constructors. Now, if you have a field that is both final and static, that's like a constant in Java. So here I have an example of two final fields in a class called circle. The first field is a static field called pi. This is a class field, and this is a constant because it is static and final. It is available to all instances of circle. Actually, the fact that it's public means it's available everywhere that circle is public. So it's public, static, final. The type is double. The name is pi, and it has the value 3.14159. So this is a constant in Java. You can't change it because it's final, and it's available everywhere because it's public and static. Oh, and note that by convention, when you have a constant, we have something that is public, static, final. Its name is written in all caps with underbars in between words. So here we have pi here, capital P, capital I, because it's a constant. Each circle instance also has its own radius. And the interesting thing about a radius is that, well, it doesn't change over time. At least the way I'm modeling it, the radius of a circle never changes. And so because it never changes, I want to mark it as final. As a matter of fact, any code that attempted to change it wouldn't compile because it would be assigning into a final field after it's been initialized. If you look at the constructor for the circle class, it takes that radius, and so then whatever code is creating the circle object will pass in the radius, and we take that radius as passed in and assign it to the radius field, and because it's final, this is the only assignment that will ever take place. Now the circle class has a behavior, has a method called getCircumference. It's going to return the circumference of that circle as a double. And the way it does it is it says, well, everybody remember from high school geometry, the circumference of a circle is 2 pi times its radius. So we express that as the number 2 times the value of pi, that's that constant, times the radius of this circle. So this is an example of how you have how you can use final fields. You can use final fields as a constant when it's static, or as a final instance field when you have a value of an object that never changes. A couple slides ago, I said that every class in Java is a subclass, either directly or indirectly, of Java Lang object. And Java Lang object provides certain methods to, therefore, all objects. So all objects have an equals method that allows them to express if they are equal to some other object. So it's called public Boolean equals and returns true or false of whether or not this object, the one that the equals method is invoked on, is the same as the object that's passed in. Now, notice that this is value equality. This isn't the same thing as pointer equality. So if you have two objects, and if you want to say, are they exactly the same object, then you would use equals equals or not equals if you want to say they're different objects. But if you want to say, hey, do these two objects represent the same thing? Let's say you've got two objects that represent the number 4 or two strings that have the same contents. Equals allows you to determine whether or not two objects have the same value, even if they aren't the same instance. All objects also inherit a method called hashcode from JavaLang object, which returns an int which represents, well, the hash of the object. This is very helpful when you're using objects as the key of a hash table, or when you're just looking to do hashing on objects. We'll see more details about the clone method in a later set of slides, but all objects also have a clone method which lets you make a copy of them. It's different from a copy constructor like in C++. Instead, the clone method, well, it's special and we'll see it later. All objects also inherit a method called getClass from a JavaLang object. And this returns an instance of what's called the meta class, which provides information about the class of the object itself. This is some kind of advanced stuff, and we might see it later in the term, but it's just another good example of things that all objects have. And another method that is inherited from a JavaLang object is a method called finalize, and this is some code that is intended to be invoked when the object is destroyed by the garbage collector. This is code that does some final cleanup before the object is ultimately returned for recycling later. Quite frankly, this is kind of a nice thing to know about the Java language. It is very unlikely that you'll ever implement one of these, and certainly it's not something that you invoke. It's something that's invoked by the garbage collector. But it's kind of a neat example of something that any object can do, and the way they express that is they put a method on JavaLang object. Now, as you're building out your hierarchy of classes, there might be some behaviors that are common to a number of different classes, but they don't necessarily have a default implementation. This is where the abstract keyword in Java comes in. Now, when you declare that a method is abstract, you're saying that, well, anything that implements this class or anything that provides this class's contract must have this method. But there's no default implementation of it. It's up to the subclass to provide an implementation of it. And this is very useful when you're modeling something where everything has that same behavior, takes in those same parameters, will return a value based on that. But different subclasses can do it in a different way. Because there is no implementation, you just declare the signature of the method, so preceded by the abstract keyword. So it'll be abstract void, do some stuff, and take an integer, that kind of thing. And whenever you have an abstract method, you must also make the class abstract because you can't instantiate that class because there's missing behavior. Right? If you could instantiate that class, you could say, new thing which has this incomplete method. If you went and then called that abstract method, the JVM wouldn't know what to do because there's no implementation specified. So it's very important that when you have an abstract method, the class itself must also be declared abstract. Now, of course, some other class could subclass the abstract class, provide an implementation for the abstract method, and then you can instantiate that. But when you have a class that declares an abstract method, the class itself must still be declared abstract. Oh, and note also that abstract classes, like I said, you can't instantiate them, but they can still have a constructor, which is a little strange. Basically, hey, there might be some state that is required to be initialized, and you'd want to do that through a constructor. You can have an abstract class with a constructor. It's just that the only code that will call that constructor is the constructors of the subclass that then call their parent class's constructor to initialize that context. So we talked about abstract methods and abstract classes. There's also something in Java called an interface. It's kind of like a class in that it has a whole bunch of methods, but basically all of the methods are abstract. All you do is provide the declarations of the methods. You don't provide the implementation. Actually, that's not exactly true. You can have what's called a default method inside an interface, which does provide some implementation, but for the sake of learning and understanding interfaces for the first time, let's ignore that fact. So you've got an interface, and it declares that, hey, anything that implements this interface, any class which is going to provide this interface, must provide implementation for, well, all the methods in the interface. And the way you do that mechanically is that when you create your class, you say that the class implements, you use the implements keyword, specify the name of the interface that it implements. And that code will not compile until you provide an implementation of all of those methods. In Java, a class can have one and only one superclass. However, it can implement multiple interfaces, meaning that it can provide behavior for multiple interfaces, even though it only extends one superclass and therefore inherits the fields, the state of that superclass. You can have a hierarchy of interfaces. You can have one interface extend another interface. And all those methods that are declared in the interface are implicitly public. It doesn't make sense to have protected members of the, certainly not private members of the interface. You can declare fields inside an interface, but they're essentially constants, right? They are public, static, and final. You can't assign a value to a field in an interface in some other class. But just like classes and primitive types, I suppose, an interface is a type in the Java type system. So you can have a variable of a type interface. You can have a parameter of a type interface. It's really a nice abstraction in the language. And we'll be seeing lots of examples of these, especially in what are called the collection classes, when we learn about standard APIs for grouping objects together. Another aspect of the Java language that I want to cover, what are called annotations. Now, annotations are little tags, if you will, that you can put on classes, fields, and methods that provide some additional metadata about that. It's sort of like a Java comment. It basically specifies some additional information about that programming element, about that class or field or whatever. But these are available at runtime to the code, and then they're often used by other code to note things like, oh look, this is a test method right here. I should run it as a test, or hey, this method overrides another method, and if it doesn't, issue a compilation error. So they look like those tags that we saw in Java docs, but they're not inside comments. They are just right before the program element. And there are a ton of annotations out there, and some ones that come with standard Java that are in the Java Lang package are things like @deprecated, which means that a program element shouldn't be used anymore. So maybe this is a method that is going to go away in a future version, or is something that has been known to be unsafe, so you shouldn't use it. @override is a good annotation to use because it specifies that a method overrides a method of its superclass. The reason this is so useful is that if for some reason the method that you inherit, the superclass from the superclass, changes, you want to make sure that, so let's say a new parameter is added to it, or its name changes. You want to make sure that in your code, that subclasses, that you are still overriding the method that you thought you were. Because remember, if some code is programming to the interface and is working to the superclasses API, if the API of the superclass changes, and then the code that is using the higher level class, the superclass, if that client code is changed to use the new name of the method, for instance, and your code hasn't overridden that method, then the behavior will change for the client, and the client won't realize it. Similarly, there is the @suppress warnings annotation, which instructs the compiler to not issue warnings for code in a particular method. An annotation can also have what are called elements to it, which is just some additional parameters to the annotation to specify more information about what's going on. So for instance, suppress warnings, you can tell it what kinds of warnings you want to suppress. Here's an example of using annotations. Here we have a Java class that's got some annotations. It starts out with a javadoc comment, though, which is nice. Javadoc has the at lowercase deprecated, which lets the javadoc express that it's deprecated. But then you can also use the at capital D deprecated annotation right before the class declaration to specify that the entire class is deprecated. Another couple of examples. Here we have like this equal method, which uses some other deprecated APIs. And we can suppress that warning for this code, meaning, yeah, compiler, please don't complain. I know I'm using a deprecated API. It's okay in this case. Also, the equals method, because it overrides the equals method provided by Java-lang object, we mark it with at override. Again, if anything were to change about the equals method they inherit from Java-lang object, which yes, seems very unlikely, but if it did, this code wouldn't compile because it no longer overrides the equals method as expected. It's a nice check. So we've learned a lot about object-oriented programming. Here are some differences between object-oriented programming in Java and C++ that I wanted to highlight. Once again, Java doesn't have pointers, right? You can allocate objects, but you can't perform arithmetic on the pointers, and you don't free it yourself. You don't delete the objects. The garbage collector takes care of that for you. The terminology that you'll see used with Java is different when it comes to objects and classes. So for instance, in C++, we talk about member functions. They're called methods in Java. C++, we have member variables. They're called fields in Java. And then Java uses instance methods instead of virtual functions. Java doesn't have template classes. It's got generics, which are a lot like that. And we'll learn about that in a later lecture. Maybe they'll come in the future. In C++, by default, when you have a virtual function, you have to declare it as virtual. It works the other way in Java. By default, all methods are instance methods. You have to put static to make it a non-virtual method. In Java, you don't explicitly allocate objects on the runtime stack. It might happen underneath the covers with a JVM, but it's not like the programmer says, "Oh, I want this object to be on the stack versus this one to be on the heap." Java also doesn't offer multiple class inheritance. You can inherit multiple interfaces, but it's all single inheritance for classes, and that makes things a little bit easier when it comes to managing state. In Java, you have public and private and protected and package level access, but there isn't a concept of like friend classes like there is in C++. You can't say, hey, listen, there are some of my fields and methods that someone off in a different package can access, but they're not protected. It just gets too confusing. So that's something that Java just doesn't have. And again, there's no explicit memory deallocation, so you can't free an object once it's been created. That's up to the garbage collector to do for you. And garbage collectors are very, very smart. There's a couple of decades now of Java programs out there, and the garbage collector is a piece of software that has just seen a tremendous amount of optimization over the years, and they're also very tunable. And so then for most programs, of course, you can always find degenerate cases where a garbage collector will get in the way, but most programs do very well with Java's garbage collector, and they're so much more simple because the developer doesn't need to worry about it. Not operator, the bang operator only works on booleans, and so if you want to check for something, if a reference to an object is null, you say whether or not it equals null instead of saying a if not object. Unlike in C++, where you have header files where you declare the contract for a class in a .h or .hpp file and then the implementation in a .cpp file, everything's in the same file in Java. I think that keeps things more simple. And in Java, all classes inherit from objects, so there is a root class, where in C++, or at least original C++, there was not. So, in summary, there are a couple of things that I hope you take away from this slide deck. An appreciation of object-oriented programming and how it separates the interface to a data from its implementation, right? Separating out that what from the how via the contract of its methods. Java classes are made up of fields that hold data and methods that perform work, usually on that data. And that Java has access modifiers to control what other code can see particular methods and fields within another class. In Java, static members are associated with the class itself, and all instances of that class share the same value of the static members. And then there are also instance members that are associated with objects, with individual instances of the class. And finally, in object-oriented programming with Java, the functionality of a class can be extended through inheritance by having one class subclass another, and then also by having a subclass override the methods inherited from its superclass. And so that's it. Thank you for taking some time to explore how concepts in object-oriented programming like classes, interfaces, methods, and fields are expressed in the Java programming language. Object-oriented programming is really a core component of contemporary software development, and I hope that these slides have given you a better idea of how to use objects and build some classes of your own.